Good morning, everyone. I am Ashi Patidar from second year. Now, I would like to invite Mr. Ajay Satpute sir for an expert lecture.
All right. Good morning, everyone. So, can I start?
Yes, sir. Yes, sir.
Yes, sir. It's always a pleasure. I'm going to mute IIST guest account so that there is no disturbance from their side. But if you want to speak up, please make sure you can unmute yourself and you can talk again. All right. So again, good morning. It's always a pleasure to interact with IIST. So I had been there, I think, a couple of years ago, just before the famous 2020 year, and I'm a big fan of your faculty, basically, Dr. SAMATHA Singh Ma'am and Ms. Farhin Ma'am. What I have found in those this great personality that they care about their students, and that is extremely important thing, because if a teacher cares about the students learning, then the student will become a better student, okay, and improve something in their life. I think ma'am had mentioned during the introduction that I'm an expert speaker. I don't believe that I'm an expert, but I'm a very good student. So I keep learning, and probably I'll be able to learn something today because of your help. This topic is role of simulation software in process industry, right? So the question is, can we do plant design without using simulation software? So when I say simulation software, I mean HANDBOok, EDR, fluid flow, PipeNet. So there are n number of different simulation softwares available. We'll be only focusing on process simulation software because other disciplines have their own simulation software. Yes, to answer this question, the simple answer would be no, we cannot. And probably we can conclude this session by with this answer. But anyway, we are going to spend another 30-40 minutes discussing why we cannot. Right? So let's say this simple example. So actually, I had planned last weekend to give a detailed presentation, like what are the different softwares available when they were they came in the market and how they will progress. But while I was preparing that this presentation, I myself got very sleepy. So I thought I should not do that with you guys. Okay, so I made this thing very simple. And whatever problems, project problem that I have come across during my 20 plus years of experience in process industry, I have taken a few. And then with those examples, those project problems, I'll be making my point that why simulation softwares are important, and we cannot really do anything about without using the software. Okay, so this particular example, so benzene, so there is this vessel which is operating at say 1 bar gauge pressure, you see here, and we want to load it to say some road tanker or send it to some other place at 30 meter cube per hour and at say 4 bar gauge pressure. So when I say that we need to design this system, so I mean that I need to design this pump, right? I will decide what is this pump suction line size, pump discharge line size, what is the pressure drop. You can see there is one control valve. Probably this is the level control valve. Then there is this flow orifice. There is minimum flow control valve. So all this sizing we have to do. And we can very well do that using Excel, because this is quite simple system, right? You can use the Darcy-Weisbach equation to get the pressure drop values. You can use the different standards, say for control valve, you can use the SA 750101 standard and go ahead with the sizing of the control valve. Then this orifice sizing also do. So we already have a lot of equations available, which we frequently use in process industry. And we can use Excel file to do this sizing. Okay, also we can do the same thing using Aspen HYSYS or any other commercial software. So we have this pipe 100, that is the pump suction. Then there is this pump. So we can find out what is the in-passage available. We can find out what is the head required for the given flow rate. And then this minimum flow control valve sizing we can do. The level control valve sizing we can do. The sizing, pump discharge, then pump minimum recirculation line. So all this sizing we can do using Aspen HYSYS. So in this example, in this particular case, simulation software like Aspen HYSYS usage is not really required, as the design is quite simple. So let us make things more complicated. So we have this early production facility. So in oil and gas, you cannot really do away with early production facility or EPF. So whatever 2-phase or 3-phase fluid that comes out of the earth in the oil well, it goes to this Christmas tree. So there is this wall, choke wall. So upstream, you can imagine very high pressure, say 5,000 psig. And then downstream, the pressure would be 500, 600 psig. That goes to the separator, preheater, heater. So it goes to many, many places. The objective of this early production facility is to separate the gas, oil, and then produce water. Oil is sent to the refinery. Produced water is again pumped back to the same reservoir. And then gas, if it is useful means if it makes sense to process that, purify it, then it is done. Otherwise, it is just burnt. So this kind of design of early production facility, we usually use Aspen HYSYS and Aspen EDR. Aspen HYSYS for the process simulation. EDR is for heat exchanger side. So this is a you can say PNID, simple PNID for the same system. From the time point from the oil well, you have this say 2-phase feed, oil and gas goes to the preheater, is the heat exchanger, shell and tube. Then it goes to the heater, and then temperature is increased in the heater. It goes to the separator. Vapor goes out from this vapor line through the pressure control valve, PCV, and then oil is pumped out using these 2 pumps, one running, one standby. It goes through the flow orifice. It goes to the LCV, level control valve. Then through the preheater, it goes out to the storage tank, okay, or wherever it wants to. Now this system, we can very well simulate in Aspen HYSYS. So it will have this preheater, then the heater, separator, all the sizing we can do using Aspen HYSYS. The heat exchanger, preheater sizing also we can do using Aspen EDR. From EDR, we can get the mechanical drawing of the heat exchanger. Okay, this is the tube sheet layout. In order to depressurize this separator, so that sizing of this orifice, precision orifice, can also be done using Aspen HYSYS. Now the heat exchanger or the this orifice sizing for the depressurization, we cannot really do using Aspen using Excel calculations. It is not like we cannot do, but if you choose to do that, the accuracy will not be there. Right. So let us run this early production facility, what we had done in steady state. We can run that in dynamic mode. You see here the simple system there. So 2-phase feed. It will first go to the preheater, heat exchanger, then heater, then separator. The FIC, this is the flow controller. What it is doing? It is throttling your flow control valve in order to get the required set point flow. Okay, so here you can see the set point is now 20,000. We want to maintain 20,000 kg per hour flow in this line, right? These 2 plots, what you see here, FIC, the green one is the flow rate, and then blue one is the opening of FCV, flow control valve. And the plot here, right side bottom, that is for the LIC. So the green one is the level in the separator, and the blue line, that is the opening of opening of this LCV. So if I change the set point, let us say for 20,000, this is the plot. If I change the set point from 20,000 to say 18,000. So immediately we'll see the changes happening. So we are able to get 18,000. So how do I get 18,000? By throttling the flow control valve more, right? Before it was something 80% open, now it is 74% open. And the impact on the level of the separator and then opening of this LCV, so that is also reflected here. If I again change back to 20,000, the system will go back to this original situation. So now you can imagine if you don't do the simulation in Aspen IIST Dynamics, okay, if you wanted to use say Excel, you will not be able to get this kind of output. So this gives you the real picture that if you are designing the system, but how it will behave when you actually run the system. So if you're using Aspen IIST steady state, so you can make the steady state model. If you're using Aspen IIST Dynamics, you can actually run the plant and see what will happen if you close it XP-1, ESTV valve. What will happen if the PCV, pressure control valve, becomes fail closed? So all these scenarios you can study in simulation software that you cannot really do using your normal Excel. We go to the next example. Here also we are using Aspen IIST Dynamics. This for the compressor surge analysis. So the system is something like this. You have this gas stream number 1. So what does stream number 1 pressure is? 7 bar gauge, 85 degrees C. And what is the composition? You can see composition is methane. So this is basically the sales gas. You want to compress from 7 bar gauge to, you see the last point here, 12. The pressure is 15.6 bar gauge. So that is my problem state. Using Aspen IIST software, so we can do the steady state simulation. But if I want to run it in dynamic mode means, let us say we are having this event scheduler. So for first 5 seconds, I don't want to do any tripping of this compressor. So after 5 seconds, the compressor will get tripped, and after 7 seconds, both suction shutdown valve and then discharge shutdown valve, so those will be closed. So this we can simulate in Aspen IIST Dynamics, and we are going to run it for, you can see here right side bottom, we are going to run it for say 60 seconds. So we know that, and this red point you can see that is the operating point, right? So let us see what happens. So till the time is say 5 seconds, nothing will happen. The operating point will not change. But as 5 seconds are over, the compressor is going to get tripped. And then the RPM, you can see here, RPM is now 5.3, now it is 4.900. So the compressor is slowing down. So this kind of simulation we can do. And what is the objective of this simulation? The objective is we need to safeguard this compressor. So that we can do using this anti-surge valve, ASV. If I have the adequate capacity ASV, like say in this case we are using 500, so the compressor will not cross the surge curve, meaning compressor will not have any damage, mechanical damage. But if you use a small size or small CV ASV, anti-surge valve, then this 10-15 CR cost compressor may get damaged. So that we can say with doing this study. Okay, this is called as compressor surge analysis. So this we can do using Aspen IIST Dynamics. Now let us move to the cooling water network design. Again, the software here would be fluid flow liquid module. So what we understand by cooling water network, you must have seen cooling tower, right? So what is the objective of the cooling tower? So cooling tower will take warm water, say 40 degrees C temperature water, and then it will cool down to maybe 30 degrees C. So that 30 degrees C water will be sent to the cooling water supply pumps. And then this 30 degrees C water will be sent to the entire plant, to different heat exchangers. So in one side, there is utility cooling water, and the other side would be the process fluid. So let's say hot methane gas you want to cool down in heat exchanger number 1. So the water will be supplied from the cooling water supply pumps. So similarly, heat exchanger 2, 3. So there are total 11 heat exchangers in this figure. We can simulate this such a system using fluid flow software. It is again hydraulic simulation software. So this is cooling tower basin, that is the starting point. And then water goes to this 2 pumps, one running, one standby. And it goes through different heat exchangers. So in this example, I have shown only 3 heat exchangers, but you can have n number of heat exchangers. In one of the projects, we had modeled 170 heat exchangers. Okay, it was for one of the refineries in Madhya Pradesh. And then the temperature rise is at 10 degrees C. And then the warm water will get collected in this return header. And again, it will go back to the cooling tower top. And from top to bottom, again, temperature drop will be there because of this mass transfer with the ambient air. So this is basically the system. The line size is line length. Okay, that will be as per the piping isometry. The objective of this study would be to check the adequacy of, let's say, existing system. So you can see the pump suction line is 12-inch, and then velocity is 1.1 meter per second. So as per API 14E, this is the standard that we use for the line sizing. So this velocity is okay. That means this line size 12-inch is also okay. Similarly, pump discharge. So pump discharge velocity you can see 2.7 for 5-inch. Again, it should be close to 2.7 meter per second. So which we are getting. So this inlet is 12-inch, and then outlet is 5-inch. So that will be not 5-inch, sorry, it will be 8-inch, this one. So that will be adequate line sizing for the pump discharge line. You can do this single pipe pressure of calculation using Aspen, using Excel. But when you're talking about the simulation of the network, then you cannot really do that using Excel. So you have to use some simulation software like fluid flow. We can also do FIREWATER network design. So what do you mean by FIREWATER network design? So let us say there is this pump house, right? So you have got, say, 6 pumps in that. Now we need to protect the pump house in case of fire. So how do you extinguish the fire? Using water. And that water is coming through the sprinklers. So how many sprinklers that you see here? Total 12 sprinklers are there. Now, how do I know that the pressure available for the water when it is needed would be adequate or not? So that we can do using simulation software. Now, in this case, we are using fluid flow liquid module. The typical FIREWATER system would be comprised of FIREWATER storage tank, then FIREWATER supply pumps. So typically one electrical, one diesel operated pump will be there, big pump, main pump, and then 2 small pumps, we also call it as jockey pumps, will be there. Here we are only considering 2 main pumps, one running, one standby. And then the discharge side, there will be one deluge valve, and then of course the piping and the sprinkler. Once you run the system and then you find out that the upstream of the sprinkler, the nozzle, the pressure is a 1.9 bar gauge, and then flow rate would be 3.3. If this flow rate is more than what we require, say 2.9 is what we require, then we can say that the pump selection is adequate. The line sizing is done properly. We cannot really do this using Excel. We have to use simulation software. We can also do the surge analysis using simulation software like PipeNet, Transient. Just look at this example. We have this pipe, okay, with the wall. This wall is closed. That's why the water is still, there is no flow. Let us say we open the wall and then water starts going from say left to right. If you suddenly close this wall, what will happen? The slug of water, okay, will be banged against this wall and it will create some pressure surge. There is this Joukowski equation. We can calculate how much pressure surge will be there. It is minus rho C and multiplied by delta V. So rho is density of water in this case. C is the wave speed, means velocity of sound in that particular liquid, and then delta V is the velocity change. Say in this example, let us say it's not water. We are talking about some other fluids, some other so some other fluid, say oil. So oil density is say 800 kg per meter cube. The wave speed is say 1380 meter per second, and the velocity change is say 2 meter per second. So this particular system has got all the potential to have the pressure surge of 22 bar. If the design pressure of this pipe is say 16 bar gauge, then the pipe is in danger if you suddenly close this valve. So it is quite serious situation, and it's a real problem. So people spend a lot of money to find out whether the system is safe, and if not, if there any is there any remedial action that we can do to protect the system. So this study is done using PipeNet Transient software. So let us say the example is crude oil transfer from storage tank to ship tanker. Say HPCL Mumbai refinery is sending the oil to ship tanker, okay, in Mumbai Port Trust. So it is quite 6-7 kilometer long pipeline is there. And the pipeline minimum maximum allowable surge pressure value is say minus 0.5 bar gauge, meaning it can withstand 50% vacuum in the pipe. And then maximum is 16 bar gauge. That is the maximum allowable surge pressure. So case one would be without any surge elevating device. So this we can do using PipeNet Transient. So you see this case. So this is the pump. This is a shut-off valve, and it goes to the tanker. So the shut-off valve, you see here on the right side. So it is taking 2 seconds to 27 seconds to close completely, meaning 25 seconds it is taking to close from say 100% open to 0% open, right? So because of that, if you run this, okay, if you run this, it will tell us that the maximum pressure that it will have is 20.8 bar gauge, and then minus or negative pressure is going to be minus 0.26. Since the minimum allowable surge pressure is minus 0.5 bar gauge, we don't have any problem with the minimum pressure or minimum surge pressure, but the maximum is exceeding 16 bar gauge, which is a concern. So we cannot let this system run without any surge elevating device. So what we do in this example, you see here. So this is a liquid surge relief valve with the set point of say 14 bar gauge. So once I add this and then run it, okay, you can see the maximum pressure is now 15.5 bar gauge. What is the maximum it can withstand? 16 bar gauge. Meaning I have made the system safe by adding one liquid surge relief valve. So there is one more thing one can do, is adding one surge accumulator. So again, if I run this and then try to find out what is the maximum and minimum pressure, you can see it is 10.1 bar gauge, maximum, minimum pressure will be 0. So which option will be better? second or third, this one. This is an expensive option because it will require the compressed gas for nitrogen cylinder, and frequent maintenance will be there, and the operator will have to be very careful with this particular system. So we are talking about a lot of money, okay, when you go ahead with accumulator option. But the second option, the one with the liquid surge relief valve, so it is quite cheap and it will solve the problem. So this way we can take a decision to go ahead with this option 2 with surge relief valve instead of going ahead with surge accumulator. All right, so the conclusion, overall it will be cheaper, better, more accurate design if you use the simulation software correctly. Now this word correctly is very important because in simulation we always say garbage in, garbage out. So you have to understand how the how simulation software is using your data. That means you must know what formula it is using, okay, what philosophy it is using. If you say that I will not go into that how software is using your information, but I will just use the data, then your design will never be correct. And with software, you must know as a minimum. So Aspen HISIS is there, Aspen EDR for heat exchanger sizing, Aspen flare system analyzer or FlareNet for flare header design, Aspen HISIS Dynamics to carry out some dynamic studies. Aspen Plus is there. So Aspen HISIS is very popular in oil and gas industry. But if you want to do projects in chemical, pharmaceutical company, then Aspen Plus you must use. Then there is fluid flow software and then PipeNet. These two are the hydraulic simulator software. And how one can learn these softwares? All right, so now this is a little bit of marketing of CONVERGE engineering. So I written one book, Process Plant Design and Simulation Handbook. This is extremely good resource for learning Aspen HISIS. So if you have Aspen HISIS installed in a laptop, and if you have this handbook, so you can learn the software very easily. It also has some chapters, 3 chapters for the dynamic simulation, two chapters for the dynamic simulation, and it will tell you how to do the line sizing, controller sizing, separator sizing, orifice sizing, how to design the entire plant, and how to run that plant in dynamic mode. So it is quite useful resource. I would suggest that you purchase this. Already more than 900 copies we have sold. People are talking good things about this handbook. Okay, it is available on Amazon as well. There is this new book that will be published in couple of months. Compressor surge analysis is also extremely important and useful book. We also carry out the process design training. So if you want to learn about process design using simulation software, you can take our help for learning it. We are getting quite a good reviews of that process design course. All right, so I'll ask the same question again. Can we do plant design using simulation software? Without using simulation software? No, we cannot. All right, so I believe we're done in half an hour. Right, any questions? Anyone has got any question?
Ajay, now, here,
Hello, am I audible, sir?
Yes, sir.
Sir, can you please repeat the objective that you told in that Aspen Dynamic software operation?
Your voice is not clear. Can you repeat your question, please?
Sir, can you please repeat that objective that you told in that Aspen Dynamic software operation?
To help me with that, there is a lot of buzzing sound. If anyone has heard this question, can you tell me what exactly is the question?
Sir, he is asking for the objective of Aspen dynamic process.
Objective of Aspen IIST dynamics.
Yes, sir.
All right. So objective is we need to, first of all, the steady state. We use Aspen IIST to model the system. And if I want to run this using Aspen IIST dynamics, so I should be able to do that. Say, for example, this is a compressor example. See that? So we already use steady state to do proper sizing, line sizing, wall sizing, etc. But if I don't use Aspen IIST dynamics, I will not be able to do the sizing of this anti-surge valve. So here we do the trial and error. If I use, instead of 500, if I use say 400 CV, okay, let us do that. So let us say I put 400 here. Let us make this thing reverse 200, make it 200, and then go to event scheduler, and then start it, then go back, and let's pull the plot, and then run it. So after 5 seconds, the compressor will get tripped. And you can see this operating point has crossed this surge curve. So we should not have the operating point crossing the surge curve. So that will damage the compressor in no time. We cannot do this analysis. What should be the size of this ASB using steady state? You had to go for Aspen IIST dynamics. Does that answer your question?
Yes.
Thanks.
Thank you, sir, for sharing your experience and valuable information with us. This was a very informative session. Thank you once again.
All right. Thank you very much, everyone. Have a nice day.